Alrighty, my friends, let's go ahead and talk about some power series and convergence. So, a power function is simply something like x to some power, like x to the fourth. So, it's basically a variable raised to some sort of power. Now, to make that into a series, we add them up because that's what a series is. So, it looks kind of like a polynomial. It's a little bit of a way you could think about it. So what makes a power series converge? So what we're going to do here is we're going to use the various tests that we already have to determine if a power series converges or diverges. And when I say if a power series converges or diverges, you're looking for the set of x values that will make a power series converge or diverge. So the thing I'd like to plant in your brain right now is I want you to consider what possible answers we could get for our set of x values. And that will become more clear, hopefully, as we go. So for this first one, I want to find the radius of convergence. That means the set of x values that will make this power series converge. So I'm going to do, I see a factorial there, so I'm going to go ahead and try the ratio test, see if that works. I mean, my first test I should do is the divergence test, but that would be the limit as n goes to infinity of x to the n over n factorial. I'm just ignoring that negative one. And that goes to 0 because the n factorial will totally dominate the x to the n. So the divergence test told me nothing, so I need to keep going. So let's do the ratio test. So the limit as n goes to infinity of the absolute value of negative 1 to the n plus 2, that's a 2, x to the n plus 1 over n plus 1 factorial over x to the n negative 1 to the n over, so flip it, n factorial. Make sure you understand the algebra there. If you don't understand the algebra there, write it down as a big fraction and then give it the old flippy flop and figure out what's going on there. The negative ones don't matter because of the absolute value. I just realized this should be an n plus 1 because that's an n plus 2. And then negative ones don't matter. X to the n plus 1 over x to the n is just x. And then n plus 1 factorial over with an n factorial. So this is like one term bigger. So we'll have an n plus 1 here. X is a fixed number. N is something going to infinity. So this is 0. So the radius of convergence is infinity. What that means is, trying to think how to phrase this. I'm just going to write a series converges for all real x. So no matter what number you pick any number you want, and that series will converge. To connect this to previous stuff, that series is going to converge absolutely, because when we got rid of the negative 1, we had convergence. The next one, again, let's do the divergence test first. So the limit as n goes to infinity, we have x over 5 to the 2n minus, not plus, minus 1. Now, as long as this is less than 1, then we're good. So, and by good, I mean then we have a chance at converging. I'm thinking ahead. So if x is greater than or equal to 5, then the series will diverge. I can state that from the divergence test because that limit is not 0 if x is greater than or equal to 5. And is it fair to say that's an absolute value? Yes. To show for what x values this will work, I'm going to go ahead and do the geometric series test. So I need the absolute value of x over 5 to be less than 1, which means the absolute value of x is less than 5, which means this is your radius of convergence right here. That's how far away we can go. So that's your radius of convergence. And then your interval of convergence, x is, the absolute value of x is less than 5, that's from -5 to 5. So any x values from -5 to 5 will cause that series to converge. I didn't write the first few terms, but I can do that also. So when n is 1, 2 minus 1 is 1, so it's x over 5. When x is 2, 4 minus 1 is 3, so that's x over 5 cubed. And then when x is 3, that's 6 minus 1, which is 5, so that's x over 5 squared, not squared, to the 5th. Sorry, I was thinking of the multiplier. So we're multiplying by the quantity x over 5 squared. So it's a geometric series because we're multiplying by the same thing every time. We need the radius, we need the common multiplier to common ratio to be less than 1. So -5 to 5 were our values that worked. Right, the first few terms, the interval of convergence. Okay, so this is the same idea as the last one. So when n is 1, 1 minus 1 is 0, so that's not, no. When n is 1, that's x minus 1, I plugged in 1 for the wrong thing, over 1. When n is 2, it's x minus 1 squared over 2 squared, which is 4. And then x minus 1 cubed over 3 squared, which is 9. So this kind of reminds me of 1 over n squared. And 1 over n squared is going to converge. 7 over n squared is going to converge. So I'm thinking we're going to have some convergence going on here, but I'm going to go ahead and do the ratio test and see what happens. The limit as n goes to infinity. I could do the divergence test first. That's going to show pretty quickly that sometimes we'll converge, sometimes we'll diverge, just depends on the x value. So we could narrow it down a little bit there, but I think I'm just going to jump right to the ratio test and see what happens. N plus 1 squared, and then I'll have x minus 1 to the n, and then n squared. Again, if you don't understand what I did there, write it as a fraction on a fraction, and then go ahead and simplify. So limit as n goes to infinity. This part just becomes x minus 1. This part, I think I can just claim that that's going to go to 1. If you don't believe me, you could go ahead and say the limit as n squared goes, limit as n goes to infinity for n squared is infinity. The limit of n plus 1 squared as n goes to infinity is infinity. So do l'hôpital. So then you'll have 2n over 2n plus 2. Do the same thing. So you'll have 2 over 2, which is just 1. So I think we can claim that. We want this to be less than 1 because it's the ratio test. So you have the absolute value of x minus 1 is less than 1. This right here is your radius of convergence, because that's how far away we can go. If you think transformationally, this helps you get your center. Your center is x equals 1. So if I can go 1 away from 1, that brings me to 0 and 2. I need to go ahead and check the endpoints. Now, I didn't talk about this on the last one because I didn't need to because it was a geometric series. But theoretically, I need to test my endpoints. So test x equals 0. So if x equals 0, I have -1 to the n over n squared. So I'm going to claim this converges by comparison to 1 over n squared. So I didn't write out like a full explanation there, but 1 over n squared I know converges. -1 to the n over n squared is less than 1 over n squared, so therefore that also converges. You could have also done an alternating series argument. that 1 over n squared is going to 0. And you have negative 1 to the n, so we will have convergence there also. Let's see what else we got. So I need to check the 2 endpoint. So test x equals 2. And if you're confused, I'm plugging it in right up here. So I'm doing, I'll show you my work a little bit more. 2 minus 1 n squared. So you're replacing the x. So that's a summation, n equals 1 to infinity, 1 over n. I wrote n factorial. That's supposed to be n squared. Silly goose. And that converges by p-series. So I include the 2. So my interval of convergence is from 0 to 2 inclusive. So I include both the 0 and the 2.